Hello, everybody. Today we have lecture number 10. And motivated by the questions after the previous lecture, I wanted to once again to speak a little bit about evolution equations and closed operators related to evolution equations. So let us start from the very beginning. And everything is so we introduced closed operators in order to prove this theorem. And actually, this is the only theorem which we are going to discuss concerning the closed operators, but still the notion is very important, and I would like to clarify what is the importance of this notion. So in the context of evolution equations, as it was at the previous lecture, so let us consider a function which is a function from time interval to some normed space x. And we are interested in the evolution equations of the following form, where A is a linear operator. So what is written here? So the derivative with respect to time, it is something like this. Yeah, but since for each time point, this is the element in a norm space X. So in order to define a derivative, we need to consider such limits. And hence, our norm space should be complete in order to have limits of such things, yes, without extra problems. So the standard setting is that we consider evolution equations in Banach spaces, not just norm spaces, but Banach spaces. Yeah, and so the left-hand side for each fixed time point t, the left-hand side is the element of our Banach space X, and hence the right-hand side also should be the element of the Banach space X, so it is natural to consider a linear operator A as a mapping from X, this is the element of X, again to X. This is again an element of X. So if we happened to consider such operator A, whose norm is finite, that is, this operator A is a bounded operator from X to X. A bounded linear operator is the same as continuous linear operator. So then one can check that this is a solution of evolution equation star with initial data U0 for some element U0 in our Banach space. And so on the right-hand side, we see the exponential function of an operator A, TA, and it is defined as a usual Taylor series. So in this case, the right-hand side of this formula is very well defined. And actually, this operator is again a bounded linear operator. And this is the estimate of the norm of this operator. So everything is very nice, very elementary, as in linear algebra. Yeah. And this is not useless, I would say. So in particular, if my Banach space is just RD, then A is just a matrix, and this is just a system of linear algebraic equations with a matrix A. And this is the matrix exponent. Okay, but not only such case is covered by this setting, but also, for example, infinite dimensional case, so X is a space of, for example, continuous and bounded functions on RD, and A is such a difference operator. It turns out that this A is related to Poisson processes, so it's a generator of a Poisson process. I don't go deeper into this, but it's an interesting operator. And it is a bounded operator in this space, and all what we have discussed here works. But of course, the above setting does not fit in the case when A is a differential operator. So the most interesting case is when A is a differential operator, for example, Laplacian. Then we have heat equation. And Laplacian is the generator of a Brownian motion, so it is a very interesting operator. So what should we do if we don't have an operator A, which is a bounded linear operator from X to X? So the idea is to modify the setting. So we modify it in the following way. We consider the operator A as a mapping from a dense subspace of X endowed with the norm of X into X. So as an example, I have written the following. We may consider Laplacian as an operator in the Banach space X, which is equal to L2 of Rd with L2 norm. And Laplacian is defined not for all elements of L2, but on a dense subspace of L2, namely the Sobolev space, with the norm of L2. Okay, so we have modified the setting. So instead of considering such operator, we consider such operator where D is a dense subspace of X. So what may happen in this setting? One thing which may happen is that our mapping A, linear operator A, is actually a bounded or continuous linear operator as a mapping from D to X. Then one can extend this operator A to the operator A bar, which is a bounded linear operator from X to X. This can be done by theorem for 9. I will show you this theorem. Yeah, so if we have a norm space and then subspace, and if we have an operator which is bounded as a mapping from D to somewhere, then we can extend it to a operator from X to the same space, A bar, and the norm is preserved. So in this nice case, we can come back to the original setting by theorem 4.9. And actually this theorem is very useful in the following context. So it's sometimes very convenient to define some operators on a dense subspace if we consider a space of some functions. Then we may consider a dense subspace of nice functions, such that when we define the operator on D, we may write down an explicit formula how A acts on good elements which belong to this subspace D. And then using this theorem, we may extend this operator to the whole space. Probably we're not able to provide the explicit formula for each element of this space, but we know that the operator is fine and is defined on the whole space. So this is sometimes very convenient. But again, taking into account, keeping in mind differential operators, this approach does not work for differential operators usually. And we have seen it in example 4.26 when we have considered the operator of first derivative. So what should we do in this case? We have to accept that bounded operators are not enough for many interesting problems. So we have to deal somehow with unbounded operators, so discontinuous. And we should hope that at least some of them are not totally bad and we can do something. So the idea is, okay, let us extend or let us weaken the notion of continuous operator so that we consider a bigger class of operators, which may be continuous, maybe not, but still not that bad. So this leads to the notion of closed operator. And I recall you, it was defined in the previous lecture. So we have two norm spaces. We have D, which is a subspace. So generally, no word about if it is dense or not, just a subspace. And the operator A as a mapping from D to Y is a linear operator. We define its graph, and we say that this couple, so A and its domain of definition, is a closed operator if its graph is a closed subset of this direct sum. And we have also last time proved this criterion of closeness, that the operator is closed if and only if for any sequence satisfying the condition that this sequence converges to something in X, and its image under A also converges to something in Y. This implies that this X belongs to the domain of definition of the operator A, and this Y is nothing else but A of X. Okay, we also have shown that if A is a bounded or continuous linear operator from X to Y, then it is closed. And then the domain of definition of this closed operator is the whole space X. So each continuous, respectively bounded linear operator is closed. Okay. So we have weakened, so extended a class of operators which we consider. And this is an important class because equation, this evolution equation star, may be solved with the so-called strongly continuous semigroup. A strongly continuous semigroup, it is a mathematical object which generalizes the notion of exponential function of an operator in the case when A is an unbounded operator. So I mean, this object covers both bounded and unbounded, but if A is bounded, this guy is just can be just defined via the Taylor series, as we have seen already. In the general case, there is the object, strongly continuous semigroup. It exists not for all operators A, but there are some operators which do generate a strongly continuous semigroup of this form. And these operators are called generators of such semigroups. So if A is such that there is a strongly continuous semigroup generated by this operator, then this semigroup gives the solution of such evolution equation exactly as in the case of ordinary differential equations in finite dimensional spaces. And it is also known that if we have a strongly continuous semigroup generated by operator A, then this operator A must be a closed and densely defined operator. So to solve such equations in the general well-developed setting of Banach spaces, so everything happens in a Banach space X, we really need to have closed and densely defined operators A. In particular, my previous example with Laplacian, so this guy, it is a closed operator in this space. And of course, this is a dense subspace of L2. Okay, let us go further. So this is a motivation that closed operators are very important because with the help of them and with the help of semigroup theory, we are able to solve such equations. One more remark. So in order to make A a closed operator, one should carefully choose its domain, definition D. Because once again, so what does mean that the operator A is closed? This means that its graph of A is a closed subspace of this direct sum. And of course, if you make D smaller, then you may lose this closeness. So D should be sufficiently large to provide a closed operator. So this leads to such notion as a closure of operator. That is, this is the smallest closed extension of a given operator A. If we just take an operator with some domain of definition, we may think about closed extensions of A. In particular, we may take the graph of A as a subset of this space and close this set in this space. If what we obtain after the closure, again, a graph of some linear operator, then this linear operator is the smallest closed extension of A. But it may happen that the closure of the graph of A leads to a closed set which is not a graph of any linear operator. So not all operators are closable. And we should be careful again with domain. So for example, if we take Laplacian, defined, for example, C infinity with compact supports RD to L2. So with L2 norm to L2 with L2 norm. So this operator is not closed, but it is closable, and its closure will be exactly what I have presented before. Namely, we when we close the operator, we extend its domain of definition to this set. Okay, so as I said, it may happen that if we start with very small domain of definition, it is not possible to close properly, or there exist several different closed extensions which are, so to say, not comparable with each other. So, for example, it was, I guess, in the chapter 3 when we considered orthonormal bases. We have discussed orthonormal bases which are related to different differential operators, and in particular, we considered Laplacian defined. So I have not specified the space, but we may consider, for example, the space L2 with 0, 1, and we considered Laplacian, and we considered, so I also have not specified the domain, but we may take domain like all u's in X, such that Laplacian U also belong in X, and some boundary condition are satisfied. For example, Dirichlet boundary condition. So we have considered this operator, and we said that this operator has some eigenvectors, eigenfunctions, and they are given by some sign functions. But if we consider, for example, another boundary conditions, Neumann boundary conditions, then we obtain, well, the same Laplacian, yeah, but another domain. We obtain another operator with other eigenvectors. So it's totally different operator, in spite of the fact that we have in both cases, okay, minus Laplacian probably would be nicest. It does not matter for this discussion, but nevertheless, so the same formula but different domains lead to different operators with different eigenvalues, eigenvectors, etc. So you see, so if we start, for example, with Laplacian, with domain of definition, something like this, functions which are infinitely differentiable with compact support in this interval, then both Dirichlet and Neumann boundary conditions are satisfied on this set. Yeah, and so starting from this set, we cannot make a closed extension like this. So the conclusion, in the setting of evolution equations, one really needs closed operators. It is a very delicate question how to close the operators, if they are closable at all, etc., etc. And it's a very delicate question how to choose the proper domain of definition to obtain an operator which we want. And so I recommend you this literature. It's the fundamental treatise, classical treatise of this year. And I guess there is everything classical, everything about concerning the classical theory of linear operators. And also in many other books, you may find at least chapters on unbounded operators, also unbounded operators which are symmetric and lead to self-adjoint operators, also in Hilbert spaces. Okay, so it was like the advertisement that it's worth to have this notion of closed operators. And so far, this is what was shown last time. So that this notion is a weaker notion than continuity. So each continuous operator is closed. And now we would like to understand the relations between continuous and closed linear operators in a better way. So we go further. And the first remark is that we may play with the norm. So introducing a suitable norm, one may convert a closed linear operator on an original Banach space into a continuous linear operator. So theorem. So let X and Y be two Banach spaces, D be a subspace and of X, And let A be a mapping from D to Y, which is a closed linear operator. So we introduce another mapping, which is defined as follows. So this evaluated at the point x in D is defined as the norm of x in x and the norm of ax in y. The statement is that this mapping is again a norm defined on D. And this set D, which is just a subspace of X, this D endowed with this norm is a Banach space, and A as a mapping from this Banach space into this Banach space is a continuous mapping. Okay, so the proof is rather standard. That's why we make it with the slides. So I'm not going to write down anything. So proof, so it is not hard to see because of this definition that this mapping satisfies all assumptions of the definition of a norm. So this guy is a norm. Second, let us show that the set D is complete with respect to this norm. So let Xn be a Cauchy sequence in D, Cauchy sequence with respect to this new norm. This is the graph norm, the so-called graph norm. So let Xn be a Cauchy sequence with respect to the graph norm. Due to these definitions, this means that Xn is the Cauchy sequence with respect to the norm in X. And A of Xn is the Cauchy sequence with respect to the norm in Y, due to this identity. But since X and Y are Banach spaces, there exist limits for each Cauchy sequence. So there exists a limit of this Cauchy sequence in X, and there exists a limit of this Cauchy sequence in Y. Since our operator is assumed to be closed, this means that this limit X again is an element of D, and this limit is nothing else but A of X. But this means that this graph norm of Xn minus X converges to 0. And hence, we have shown that for any Cauchy sequence with respect to the graph norm, this sequence converges to X. And hence, this D is a Banach space. It's a subspace of X, so it's a vector space. And it is a complete vector space with this graph norm, so it's a Banach space. Okay, everything is clear?
Yes.
So let us show that this A is continuous. So if Xn converges to X in D with respect to the graph norm, this means that it converges to Xn converges to X with respect to this norm, and Axn converges to Ax in Y. But this is exactly means that A is continuous. So if Xn converges to X, then Axn converges to Ax. That's it. So everything is simple. So example, which we have already started to discuss. So X is equal to Y is equal to the space of continuous functions on the interval from 0 to 1, endowed with supremum norm. Then these are Banach spaces. As a subspace, we consider C1 functions. And as a mapping, we consider the first derivative. Then the operator norm on this space for this operator A is nothing else but this sum. And it is known that C1 endowed with such norm is a Banach space. I mean, it follows immediately from what we have discussed right now, but I guess it is known even before that if C1 is endowed with such type of a norm, then it is a Banach space. Okay, let us go further. remark. So remark follows from the following theorem, but nevertheless. So first, pay attention to this remark. So we have X and Y Banach spaces, and D is the subspace of X. So if A as a mapping from D to Y is a closed and unbounded, respectively discontinuous linear operator, then D is not equal to X. Because if D is equal to X, that is, we are in this situation, then A actually is a bounded linear operator from X to Y. And this we will show immediately in the following theorem. So this theorem is the closed graph theorem. So the theorem which we are going to present in this section. So let X and Y be Banach spaces. A be a linear operator from X to Y, defined on the whole X. Then the following statements are equivalent. A is continuous, equivalently bounded. Second, A is a closed operator. And third, so by definition of a closed operator, graph A is a closed linear subspace of this direct sum. So, so 2 is equivalent to 3 by the very definition of a closed operator. So just by definition. So now 1 implies 2. We have already discussed it last time and also today a little bit, that if an operator is continuous or bounded, what is again the same for linear operators, then continuity implies closeness. So let us show the inverse direction, that closeness implies continuity. So this I will write down. So once again, A is now defined on the whole space and is closed. This is our assumptions. This is our assumption. We want to show that A is continuous. So let let this norm be the graph norm on D, which is equal to X. So graph norm with respect to our operator A. Then what do we have? We have just shown by theorem 427, we have shown that if we consider the graph norm, then the domain of definition of the operator A endowed with the graph norm constructed with respect to this operator A is a Banach space. But X with the original norm is also a Banach space. And we also know that for any X in X, we have the following. The norm of X, using the original norm in X, is smaller or equal than the norm of X in X plus the norm of AX in Y. But this is just the graph norm of X. So we have two norms on X, this norm and this norm. So this norm dominates this norm, and both norms provide, so both norms make X a Banach space, so a complete space. Then we can use by corollary. It was corollary 417 of the open mapping theorem. these two norms, so the original norm and the graph norm, they are equivalent. Okay, but what does it mean? Since A is continuous with respect to the graph norm by theorem 427, which we have just proved, it is also continuous with respect to the original norm. So we have shown that A is continuous with respect to the original norm. And that's it. Is everything clear? Do you have any questions, comments?
I think it's clear.
Okay, perfect. So just to take in mind once again that we can weaken the notion of continuous respectively bounded linear operator up to the notion of closed linear operator. And once again, if a closed linear operator is defined on the whole Banach space, then this is a continuous operator. Any continuous operator defined on the whole Banach space is closed. And so the interesting situation when we consider unbounded linear operators, if they are closed, they are defined on a subspace which is not the whole X. And it is not possible to, well, how to say, to extend it to the whole X, preserving their properties, not making them worsen. Okay, so the achievement is this closed graph theorem, and remark that if we have two Banach spaces, then, so what we have shown so far, we first shown open mapping theorem. From this theorem, we have obtained the inverse mapping theorem, and also from the open mapping theorem, we have obtained the closed graph theorem. So actually, we can start from any of these three theorems and prove it independently from all the others, and then obtain all the others using only one theorem proved independently. Okay, so that's it, and probably this is the list of interesting or important theorems of, so to say, linear analysis of linear operators in Banach spaces so far. And now I'm going to discuss a next section. So one more important result of linear analysis, so one more important theorem. This is actually the uniform boundness principle, also known as Banach-Steinhaus theorem. So let us formulate the theorem. So let X be a Banach space, and this is important. And let Y be a norm space. So here completeness is not that important. Is not important, not at all. So we consider a family of operators. So the family can be very fat. So we don't care what is the cardinality of this parameter set. But all operators are bounded linear operators as mappings from X to Y. So we assume that the following holds. Sorry, it's again a star, but it has nothing to do with the previous star. I hope you survive with my numeration formulas. So the following holds. What holds? So for each fixed point of our space X, we have this estimate. So we evaluate all operators, each operator of our family at this point X. I consider this norm of the result, norm in Y. and consider supremum over all operators. So such supremum is finite, and this estimate holds for each fixed point. So it's like a uniform boundedness of the family pointwise. Then the statement is as follows. Then this estimate leads to this estimate. So this is a kind of upgrade, because here we have for each fixed point, we have this estimate, so norm in Y. And here we have the estimate for the operator norm of each operator, a lambda. This means that this family as a set in this space is a bounded set. The set is a bounded set, and we have such estimate. So we are going to prove this theorem, of course. But the statement is clear, or should I add something?
Clear.
Okay, perfect. So what one should mention that this statement does not provide us any how to say, any majoranta. So we claim that the supremum is finite, but we cannot produce any constant which gives us this supremum or upper bound for this supremum. Okay. So let us prove. So for any natural n, consider the following set xn, which is defined as follows. This is the set of all x's in X such that supremum over all lambda in lambda, norm of a lambda x, this is the norm in Y, in the space Y, is smaller or equal than n. Okay, so this xn can be represented in the following way. This is a intersection over all lambdas in big lambda, of pre-images with respect to a lambda, of closed ball in Y, in the space Y, of radius and ball around 0. We close it, then take. Okay, so if without supremum, if we just consider this, so this is the pre-image of a closed ball with respect to the mapping A lambda. And now supremum, so this condition means that we have such estimate for all lambdas. So we take intersection of these sets. So everything is clear?
Please continue.
Yes.
I have not understood. What was the question?
Everything clear, I think.
Everything is clear. I think there's no problem.
Yes. Okay. Now recall that we assume that A lambda is a continuous, each A lambda is a continuous mapping. So by definition of a continuous mapping, or different equivalent definitions, if a mapping A lambda is continuous, then the pre-image of any closed set is closed. Yeah, so this guy is a closed set, since A lambda is continuous. Agree? A continuous mapping is mapping such that for any open set, its pre-image is open, and equivalently for any closed set in Y, its pre-image is closed in X. So this is closed in X. So let me write it down. Okay?
Okay.
Yes. And then we consider intersection of closed sets. So any intersection of closed sets is again a closed set. Okay, a closed set. It's a this is just a property of closed sets, that arbitrary intersection of closed sets is again a closed set. Further, we have the following representation. X is a union over all natural numbers of such xn's. Yeah, because we have this. Okay, let me write down by this star. So due to this star, we have this representation. Okay, and now we use this important thing that X is a Banach space, that is a complete space. That is, we may apply the bare category theorem. So let me recall, we have seen it already last time. So if we have a complete metric space and X is a countable union of closed sets, then at least one of such sets cannot be nowhere dense. That is, at least one of the sets should contain an open ball. So again, bare category theorem. It's an important theorem. Oops, sorry. So by bare theorem, we have that there exists natural number n such that, okay, let me write down. There exists n epsilon positive and x in x such that the whole open ball, the epsilon around x, is a subset of xn. Okay, at least one of xn's contains an open ball. Now the next step, we show that the shift of this ball, namely such ball of radius epsilon, but around 0, also is the element of xn. So let us show it. We take any point in this ball around 0. And then two such points, x plus z and x minus z, they are elements of this, the epsilon x, this ball. Further, we may represent z in this way. This is z plus x plus z minus x over 2. Hence, we do the following. So for any lambda in lambda, we have the following estimate. The norm a lambda of z, so I didn't use brackets before, so a lambda of z, the norm in y, is, so now I use this representation of z. I use linearity of this operator a lambda, and I use properties of any norm. So it is smaller or equal than 1/2 norm of a lambda of x plus z in y plus 1/2 norm a lambda of x minus z in y. But we know that we have this. And this ball is a subset of Xn. And Xn is such that we have this. So each norm here can be estimated by n due to this inequality. So what is written here, smaller or equal, smaller or equal than n. But this means that z belongs to Xn. So we have shown what we have shown. We have shown that we have shown this. Agree?
Yes.
Okay, now I have no place anymore and I have to go to the next slide. So let me know if I'm already allowed to open the next slide. This is just to emphasize that we use Beer theorem because we have a Banach space. Okay, so next step in this proof. So further, for all or for any lambda in lambda, the operator norm of a lambda, by definition, it is supremum of norms of a lambda x, norms in y, and supremum over all x's in the unit ball in the space x. Okay, now we may make a rescaling using the linearity of A. So the idea is as follows. I take supremum over all x's which belong to p epsilon of 0. So this is a unit ball, this is the ball with radius epsilon. But if I take any x of like this, it does not matter if I take the closed ball or open ball because we take supremum, so no problem. So if we take element x from this ball, then x over epsilon belongs to this ball. Yes? Yes, I guess so. That's why here I just should, instead of x, here, I should, instead of x, write down x over epsilon, and 1 over epsilon can be pulled out from the norm. So it can be pulled out even here. Supremum, and now we have a lambda x in y. Agree? Okay.
Yes.
Okay. And now this supremum is smaller or equal. So 1 over epsilon stays. And then this supremum is smaller or equal than the supremum over all x's in Xn of the same stuff. Since this ball lies in this set, and this is a closed set, so even this ball lies in this set. Okay, but due to definition of Xn, we know that due to this Xn, we know that this stuff is smaller or equal than n. So all the rest is then smaller or equal than n over epsilon. So we have the estimate. So a lambda is smaller or equal n over epsilon. And this holds for any lambdas. N is fixed, epsilon is fixed. So we have obtained what we wanted. So everything is done. Questions, comments? Okay, seemingly everything is fine. Okay, corollary. Let X be a Banach space, Y be a norm space. We have a sequence of operators. All operators are bounded linear operators or continuous linear operators. We assume that this sequence is pointwise convergent. That is, for any X in X, there exists this limit. So there exists a limit, and we denote this limit as AX. This is an element of Y, and this is the way how a mapping A is defined, mapping A from X to Y. So the statement is that this A is again a continuous linear mapping. So linearity follows from the definition, but continuity is not obvious. So once again, we have a sequence of continuous linear operators which converges pointwisely. Then the limit is again a continuous linear operator. Now recall that in analysis 1, there is a statement that if we have a sequence of continuous functions which converges uniformly, then the limit is again a continuous function. Here we don't need any uniform convergence. Uniform convergence here would be the convergence in the operator norm. But only pointwise convergence is enough to provide that the limit of a sequence of pointwisely convergent sequence of linear or continuous linear operators is again a continuous linear operator. So proof, it is an exercise. It is a simple corollary from this uniform boundness principle. And I should mention that we also proved almost the same when we discussed, when we proved theorem for 10, but you should be careful. The setting of theorem for 10 is not the same as here, because there X was, there in this theorem, X was a norm space and Y was a Banach space, and here vice versa. So if X and Y both are Banach spaces, then we have already proved everything here. But in this setting, so Y is just a norm space. This also, the fact is also true, and it follows from this uniform boundness principle. So some people call this uniform boundness principle Banach-Steinhaus theorem. But some people say that this is the uniform boundness principle, and this corollary is the Banach-Steinhaus theorem. But actually, there are a lot of theorems proved by Banach and Steinhaus. So, which of them you specify as Banach-Steinhaus theorem? This is just a matter of taste. Okay. I guess that's all about linear operators, so mainly bounded linear operators, but okay, so these, what we have discussed in this chapter are just the very basic, but the fundamental properties of linear operators. As I said, there are not that many results actually. So this uniform boundness principle is important. And then these three, which we have discussed: open mapping theorem, inverse mapping theorem, closed graph theorem. So they are also important and useful. And once again, the remark that we used bare category theorem to prove many of these results. And there is also one more important theorem, namely the Hahn-Banach theorem. This is a theorem which is not about all linear operators, but about linear functionals. That is a particular space, a particular case of linear operators from a norm space to a field of scalars as a Banach space. So now we go to chapter 5, which is devoted exactly to this theorem. So linear functionals and the Hahn-Banach theorem. So this is one more very important theorem of linear analysis, so to say. Okay, so before we started, do you have any questions or remark about chapter 4?
I think it's all clear.
Perfect. So let us go further. So first we start with some geometric interpretation of linear functionals. So this is a presentation based on the book of Kolmogorov and Fomin. So this is just for better understanding of the objects which we are going to discuss. So it is all purely on slides, so we are not going to write down anything, but let us discuss some notions. So let X be a vector space. So we are now in the linear algebra. No topology, nothing, just a vector space over a field of scalars. And let L be a linear functional. So no words about continuity since we have no topology, only linear structure. Definition 1, the kernel of a linear functional is given by this formula. So it is the set of all elements of our vector space such that L evaluated at this point is equal to 0. Proposition that this set is actually a linear subspace, vector space, which is a subspace of X. So it is trivial because if we have two elements of this kernel of L and we have two scalars, then we consider such thing. So L applied to a linear combination. Now we use the linearity of L, and now we use that L of each this point is equal to 0 since we have this assumption. Hence, the linear combination of such elements also belongs to this set, and this is a linear space. Definition 5.3. We define the quotient space or factor space, which is denoted as co-ker of L, and this is a quotient space or factor space X over ker L. And this space is called the co-kernel of L. Yeah, so I hope that you know what is the factor space or quotient space. The two notions for the same objects. Yeah, so we consider classes of equivalences, and the equivalence is given as follows. So we take x1, okay? X1 is equivalent to x2 if and only if x1 minus x2 belongs to this subspace KRL. So this gives us the equivalence in X, and we consider all classes of equivalence. This is the factor space. So proposition. So dimension of this space, of this quotient space, co-kernel of L, is exactly 1 if L is non-trivial. What does mean L is non-trivial? L is not identically 0, because if L is identically 0, then the whole space is just its kernel. Yes. In all other cases, then if L is not identically 0, then this space co-kernel has dimension 1. So let us prove it. So let X not an element of this of the kernel of L. So since L is non-trivial, there exists at least one x0 such that L of x0 is not equal to 0. So x0 is not the element of the kernel of L. Yeah. So assume that L of x0 is equal to 1. Otherwise, we may consider another point, just make a kind of normalization. And then at this other point, L of this other point is just 1 due to linearity of L. Okay, so we consider a point such that the following holds. Probably let me. Okay. Then for every X, for every element of our space, consider the element Y defined as follows. Okay. And we see that L evaluated at y using the linearity, this is L of x minus Lx. L of x, this is a constant, it can be pulled out, times L of x0. So this is what we have, but we know that x0 is equal to 1. So this difference is just 0. And hence, this element y belongs to the kernel of L. Everything is clear?
Excuse me, will we use the condition of non-trivial?
That there exists at least one element such that L of x0 is not 0. Trivial means that it is identically 0 everywhere, on all points.
I see, thanks.
Okay. So we are here. So we have x such that this holds. We have this y. We have shown this. So the statement is that for every x, there exists exactly one element y in the kernel of L and exactly one scalar alpha from our field such that the following representation holds. So we can represent any x in this form where x0 is our fixed element which we have chosen and y is given like this, actually. So first let us show the uniqueness and then the existence. So better to say existence we have shown already. This is the existence. Now the uniqueness. So assume that there are two representations. So x is equal to such sum and for such sum for y and y prime from the kernel of L and two scalars. So from this identity we have that this holds. So alpha minus alpha prime times x0 is equal to y minus y prime. But let us investigate this identity. So if alpha minus alpha prime is 0, so that is if alpha is equal to alpha prime, if it is 0, then the left-hand side is 0, then the right-hand side should be also 0. Hence, if alphas are equal, then y is equal to y prime. If alphas are not equal, so this is something which is not 0, then we can divide this identity and we see that x0 has the following representation. But we know that y and y prime are elements of kernel. So if we multiply them with a scalar, we still have an element of kernel because kernel is a vector space. And hence x0 belongs to kernel. But yes, it is a contradiction with our assumption. So this shows us the uniqueness of representation and the existence of representation we have already obtained here. Okay.
Okay.
So we are here. So what we have for every x in our x, there exists exactly one y in the kernel of L such that x has the following representation. This is what we have already obtained here, but now we have also shown that this is a unique representation. And hence, this equivalence, I recall that the equivalence was like x1 equivalent to x2 if and only if x1 minus x2 belong to this kernel L, that is the space which is written, so over which we factorize. So x over this kernel. Okay. So since we have this representation, this means that x1 is equivalent to x2 if and only if L of x1 is equal to L of x2, because x1 minus x2, we use this representation for this point, and use linearity of functional L. So this is equal to L applied to x1 minus x2, and then linearity, times x0 plus y1 minus y2. So they are equivalent if this holds, but this holds, that is, this holds if and only if this is 0. But this may happen if and only if this guy is 0. So this is an explanation that how this factorization over the kernel, so the equivalence is actually this type of equivalence.
And the last equality is, of course, L of x1 minus x2 equals 0. Then the difference is in the kernel.
Can you repeat, please? I didn't get.
So the last equality is exactly L of x1 minus x2 equals 0. Can you hear me well?
Yes, I hear, but what is the question? So it's
not the question, I'm just commenting. So the last equality is exactly that x1 minus x2 is in the kernel.
yes.
But we needed to show.
Yeah, we show this. Okay, so there are many ways well, all things are actually obvious, and there are many ways how you show the obvious things. So of course you are right. Okay, there are many logical ways. Nevertheless, so what we should remember, if we have a linear functional, so there is this kernel L. It's a linear subspace of X. If we factorize X over this subspace, we obtain a one-dimensional space. Yeah, and factorization means that we create an equivalence. So equivalence is like this, or like this. This is the same. Okay, so a kind of conclusion, every class, so every element which belongs to this quotient space or factor space, two notions for the same object, is thus uniquely determined by its representative L of x times x0. Yeah, so each element of X has this representation where this is something from the kernel and this is something which is not from the kernel. And hence this is the one-dimensional piece which shows the difference between different equivalent classes. And hence dimension of this factor space, or quotient space, co-care of L is equal to 1. Okay, this is a kind of summary. Let us go further. So let E be any subspace of X whose codimension, that is dimension of this quotient space, is 1. So here we have started from a linear functional and obtained something. Now we forget everything and we start from a subspace, arbitrary subspace of X, such that its codimension is 1. Then there exists a linear functional whose kernel is exactly this space. And moreover, this functional is, in a sense, unique, so up to a multiplicative constant. Let us show this. So proof. So we choose any element x0, which is not the element of this E. Since we have this, E is not the whole space X. So there is an element outside E. And then for every X in X, there exists a unique representation like this due to this statement. Yeah, so it is shown as we have just presented in the previous proposition. So we have this representation. Now we define a linear functional in the following way. So set L of X is just equal to alpha. where alpha is exactly this alpha in this unique representation. Then it is obvious and one can easily show that L is a linear functional and its kernel is exactly E. I hope everything is clear.
Yeah, it's clear.
Perfect. So now let G be another linear functional whose kernel is E. Choose x0. So we have shown the existence of L. Now we show the uniqueness. So let G be another linear functional. Choose any element x0 satisfying this condition. We have already clarified that we can take any x0 not from the kernel of L. And then, so to say, normalize it in order to get this identity. Okay. So the first claim is that G evaluated at this point is also non-zero. Indeed, for every x in x, we have, what is written here, for every x in x we have, so actually we have this, where y belongs to the kernel of L. And we assume that kernel of G is equal to the kernel of L. It is our assumption. Hence, if we apply G to this identity, on the left-hand side we have G of x. On the right-hand side, taking into account that G is a linear functional, we have L of x times G of x0 plus G of y. Since y belongs to the kernel of L, which is equal to kernel of G, this is just 0. And hence G of x is equal to this. So if we assume that G of x0 is equal to 0, then it would follow that G of x is equal to 0 for all x's. Yeah, for every x we have this identity. So if this is 0, then G of x is 0 everywhere. And hence it has as a kernel the whole space X, which is a contradiction to our assumption. So we have shown that that G of x0 is not 0. And we have also shown that G of x is given like this. That is, so any other functional satisfying this condition is proportional to L with some constant. This is exactly the claim. So we have taken any subspace E with codimension 1. We have constructed a particular linear functional L satisfying this assumption. And we have shown that any other linear functional with the same kernel is proportional to L, so up to a constant. Okay?
Okay.
So we have shown proposition 5.5. Definition 5.6. So let E be a subspace of X whose codimension is 1. Every element, so the equivalence class of equivalence of the quotient space X over E is called a hyperplane parallel to E. Thus, a hyperplane M parallel to E is a set of the form. It is some element x0 plus this subspace E. That is, it is a parallel translation of the vector space E, subspace of X, by the vector x0. So this is my picture. So you have a vector space X. So you have a subspace E. You take any vector which does not belong to E, and you make this shift. And you obtain a hyperplane which is parallel to E. And this, so each hyperplane is nothing else but the class of equivalence of this, so elements of this quotient space.
Oh, excuse me. And,
Yeah.
do we take x0 not from E, or we can take x0 to be anywhere vector.
Well, if you take x0 in E, it is also okay, but
Mhm.
then the
It's
hyperplane will
not trivial.
coincide with E. So
Mhm.
that's it. Of course,
Thank you.
of course. So remark, so if L is a non-trivial linear functional, then we consider its level set. For example, the level set with the level 1. So it's the set of all x's such that L evaluated at x is equal to 1. So then this is just a hyperplane which is parallel to the kernel of L. Because you just choose any x such that L of x0 is 1. And then for every x in x, we have this representation. As we have already shown in previous propositions. So we have done it already several times, this decomposition. Hence, this level set with level 1 can be represented in this way. So all x's such that they have the form x0 plus y, where y belongs to the kernel, and hence this is a hyperplane which is parallel to the kernel of L. So all level sets of linear functional, of any fixed linear functional, they are different hyperplanes which are parallel to the kernel of this functional, and they are actually the different classes of equivalence in the quotient space, where E is the kernel of this linear functional. So this is the final geometric interpretation of the whole story. But I think we have something. So let E be a subspace of X with codimension 1. Let M be a hyperplane parallel to E. Then there exists exactly one linear functional L, such that its level set of level 1 is exactly this given hyperplane. Well, this is an exercise just to understand all the definitions and all argumentation which we have already produced. Okay, so hopefully you have some impression, so like how linear functionals are related to hyperplanes. What is the kernel of a linear functional? So summary. If we have a linear functional, we consider its kernel. It's a vector subspace of a given vector space X with codimension 1. We may consider also a factor space, and then classes of equivalence of elements of this factor space, quotient space, are just nothing else but hyperplanes of level sets of this linear functional with different levels. And these hyperplanes are all parallel to the vector subspace, which is the kernel of this linear functional. That is, linear functionals have very nice level sets. They are hyperplanes. Okay, conclusion. There is a one-to-one correspondence between linear functionals, non-trivial linear functionals, and hyperplanes in X that do not contain 0, origin of the vector space. That is, hyperplanes which are not vector subspaces themselves. ML is a level set of level 1. Yeah, so as here. Okay. So are there any questions or comments? Okay, let us go further. And yes?
If our hyperplane contains 0, then our L must be trivial.
Yes. No, because hyperplane which contains 0, it does not mean that we have the complete space. Yes. So if a hyperplane contains 0, then it can serve as the kernel of some linear functional. Okay, as a level set of level 0. But then there is not a unique linear functional, but up to a multiplicative constant.
Okay, I see. So if we want to have a one-to-one correspondence, we need to omit such,
Yes.
exclude such hyperplanes, and then it's uniquely determined.
Yes.
Thank you.
So let us go further and let us make some preparations for the formulation of Hahn-Banach theorem. And I want to stress once again that we are still in the pure linear algebra. We have just vector spaces, and that's it. No topology, and hence no continuity, nothing. Just linear structure. So definitions, some definitions. So definition 5.8 part 1. So let X be a vector space. So we consider, as usual, also over the field of real or complex numbers. A mapping P from X to non-negative numbers is called a semi-norm on X if these two requirements are satisfied. So this is a absolute homogeneity that P of alpha X is the same as absolute value of alpha times P of X for all alphas and all X's, and triangle inequality. So if we have a norm, it is a semi-norm. If we have a semi-norm, it is a norm if and only if P of X is equal to 0 implies that X is equal to 0. Okay? You remember? I hope we have discussed it already somewhere. So
Okay.
Next part of definition, we consider the real case. So a mapping P from X to all real numbers is called convex if the following inequality holds. So we take 2 points xy in X, and we take T from this interval. So we consider such convex linear combination of X and Y, and P applied to this convex linear combination is smaller or equal than. So if a mapping would be linear, then this would here would be identity, but it is not supposed that the mapping is linear. But we have such kind of inequality. The mapping does not need to have positive values. Yeah, also negative values are allowed. Okay. Third part, again, real case. A mapping P from X to real numbers is called sublinear if homogeneity, but not absolute, but just positive. So this identity holds for all, but only non-negative alphas and all X's. And triangle inequality. Some explanations, example, so norms, semi-norms, and linear functionals over R are sublinear. Agree? So
Yes.
if we have a linear functional, then this holds for all alphas, and this holds for all X's and Y's. And semi-norms and norms, yeah, from what is written here, one can get what is written here. For each sublinear mapping is convex. Indeed, we consider T between 0 and 1. We consider P of such a convex linear combination. Then by triangle inequality, for sublinear mappings, we use triangle inequality. This is smaller or equal than this sum. But since T is between 0 and 1, these things are non-negative. And hence we use this positive homogeneity that this guy is equal to this guy and this guy is equal to this guy. And hence we are back to the inequality here. Okay, and one more remark. Each sublinear mapping, so mapping satisfying this, with additional property that P of minus X is equal to P of X is a semi-norm. Yeah, so what is the difference from here and here? Yeah, so here we have only for positive alphas and here for all alphas, but with absolute value. So for positive alphas, we have these two things are the same. For negative alpha, we may represent alpha as minus absolute value of alpha, and then p of minus absolute value of alpha times x. This is absolute value of alpha, p of minus x, which is, under this assumption, p of x. So sublinear with this extra requirement means that this is satisfied, and it also means that actually the mapping takes only non-negative values. Okay, so now we have at least time to formulate the Hahn-Banach theorem. And the first, so may I go further?
I think yes.
Okay, so we formulate the theorem first for this case. So let X be a vector space over R, sorry, over real numbers. Let P be sublinear. Let X0 be a subspace of X, and L0 be a linear mapping defined on this subspace. And this linear mapping is dominated by this sublinear P. Okay, so we have a linear functional linear mapping which is defined only on subspace and is dominated by some sublinear mapping. The statement is that we are allowed to extend this linear mapping L0 to a linear mapping L on the whole space, which still remains to be dominated by sorry, so there is a typo. It is dominated by P. That is L is an extension of L0, so L restricted to X0 is as it was before, that is L0. And we have this inequality now not only on X0, but on the whole space X. So this sublinear mapping P remains to be the majoranta, so the dominating mapping. Okay, so this is an important result which allows to construct extensions of linear functionals such that their properties remain to be good. So at the moment,
this version is a bit more general. Yeah, I think often this theorem is presented with so we can extend the functional with preservation of the norm. And this is a bit
but
more
norm it is
general.
already some topology. At the moment, we live without any topology. We just have two mappings. One is linear, one is sublinear. And sublinear mapping dominates a linear mapping, which is defined. So you see, P is defined everywhere and is sublinear. L is a linear mapping, but defines only on subspace. And then we are allowed to extend L0 to a linear mapping on the whole space with the same upper bound, so to say. Again,
Yeah,
so far,
if we add some more parts, we get this more common
yes.
formulation.
It's a corollary. Yes, it's a corollary.
Yeah, thanks.
Yes. But nevertheless, so the nature of Hahn-Banach theorem, it is in linear structure that one does not need any topology in the proof. So this is the standard formulation, so to say. Okay, so we are dealing with linear algebra. So this is the theorem, and so it is supposed to prove the theorem, but I guess our time is over for today, and the proof is not in 3 lines. So I suggest we start with the proof at the next lecture.
Yes.
So do you have any questions or comments so far? Okay, seemingly no. So my plan for the next lecture is to discuss Hahn-Banach theorem in its different forms for real and complex numbers, of geometric interpretation, and many useful corollaries. And actually, the Hahn-Banach theorem is a very crucial result which allows to deal with dual spaces, and linear functionals, dual spaces, etc., etc. So this is really a cornerstone here. Okay, so I stop the recording.
Excuse me, can I have one simple question maybe?
So could you please repeat?
Can I please have one question?
Yes, sure.
Can you please return to the place where we had of L0? Sorry, can you please back?
I don't understand what we are searching for.
Yes, I also cannot tell. Can you please back? I will tell you. Sorry. Even no, even more. One more again. Thank you very much. So we have projection with for every linear functional we have ML, yes?
Yes.
But I can see how we have built it, but can we assure that for each what I say, maybe we can have different x0 for this representation.
Yes.
But
Definitely.
then it will not be projection if for one air we can.
No, wait.
but-
I have a picture. Yeah. So if instead of x0 you take another x0 tilde, you obtain the same hyperplane. I didn't say that x0 is the same, but the hyperplane is the same.
Okay. Thank you very much. Yes. Now it's clear. Thank you very much.
Welcome. Further questions?
Excuse me. Since the linear functional has one dimension for codim, so this means that if in Hahn-Banach theorem we just extend one dimension.
No. Wait a minute. No, it's a good question, but no, the answer is no. I mean, it is one of the possibilities, but it is not assumed. Let us look at the statement. So if we have this operator, this linear functional, its codim, so dimension of the corresponding factor space, so its codimension is 1. But we are in this situation. We have just some subspace, and we have a linear mapping defined on this subspace. No words about the codimension of this subspace. So actually, the proof of the Hahn-Banach theorem is as follows. I'm not going to now to start with the proof, but the idea, not the idea. So I can mention that we can take even a one-dimensional subspace of X, define a linear functional there on a one-dimensional subspace. So by hands, it's very easy. So home task, by the way, home task. Or right now, like exercise. So my space, okay, or X, does not matter. So this is just R1. So what are all linear functionals? On X. This is my question. I guess you should answer immediately.
With any point, for example, x0, then the linear functional has a form of L equal to alpha times x0. And the alpha can be determined by the relation between x and x0.
Yes. So let me write down carefully what you have said. You are completely right. So if we have any X in X, it has the form, let's say, Tx0, where x0 is a fixed point. point in X, and T is just a real number. Yeah, so from our field, so to say. Yeah, so we take any C in R and define L such that L of x0 is just C. And then by linearity, then L of x is just L of tx0. This is T times L of x0, and this is just Tc. That's it. That's all what we can. So these are all possible linear functionals. Okay, so what says the theorem of Hahn-Banach? We take a vector space, probably infinite dimensional, take any of its subspace, probably one-dimensional, take any linear functional defined on a subspace, and dominate it by something sublinear defined on the whole space. Then we can extend this linear functional to the whole space and such that the domination is preserved. So it's a really very powerful tool. You may start from here and extend to an infinite dimensional vector space, probably. Okay, so home task then would be what happens in RD. So you have a finite dimensional space. So how all linear functionals on RD look like. And I guess you also may answer immediately, but let us keep it as a home task. Okay, so just feel how cool this theorem is.
I see. Thanks.
Yeah, so a small comment that the geometric interpretation of linear functionals, which we have discussed before, is needed because later on we will discuss the geometric interpretation of the Hahn-Banach theorem. That's why, but I think it's also, even without any further applications, it's good to understand the meaning of linear functions, geometrical meaning. Yes, so I have interrupted you. Yes, please make your comment or question, give a question, ask a question.
Yeah, for me it's clear. Thank you for your nice explanation.
Okay, some further questions from the others? Okay, seemingly not the case. Then thank you for being here and